Hello everyone, this video covers section 9.9, the book. So this is section 9.9. It's called the phase plane for linear autonomous systems. And you technically already know how to solve this. There's just an extra steps or a couple of extra steps you have to do. So recall we did this before. You have a system of linear equations like this, x1 prime equals to 4x1 plus x2, and then x2 prime equals to 2x1 minus x2. Remember that to solve these problems, you have a matrix A, which in this case is a 4, 1, 2 minus 1, and then you find the eigenvalues lambda 1, lambda 2, and then the solution to x of t, which remember this was x1, x2, this was equals to c1 e to the lambda 1 times some eigenvector here, so eigenvector, and then c2 e to the lambda 2 is a t here, and then another eigenvector, and this depended on whether these were real, complex, or repeated, and we only did examples where they are real, when they don't repeat, or they are complex. So you still have to do this. This is exactly still the same thing. The extra thing is that we're going to analyze what the eigenvalues are actually doing to the system, and we're going to focus on a very specific type of system of equations, which is called an autonomous system. An autonomous system is a system that looks like this, this is pretty much the same as this right here, because this is technically x1 prime, it could be x2 prime, where these functions do not depend on t. Notice that this by itself depend on t, so x prime depends on t and y prime depends on t, but the right side doesn't have a t on it. So if the variable t is missing here, this is called an autonomous system. An autonomous system has something called equilibrium points. So we have equilibrium points. The equilibrium points are going to be all the values of x and y where f of x and y is equals to 0, and also g of x, y is equals to 0. Now, we're going to focus only on the case where these functions are actually linear equations, because they don't have to be linear equations. And if these two are linear, pretty much the equilibrium point most of the time is the point 0, 0, but it doesn't have to be. So for example, the problems we did before, notice that these are linear equations. So these are the type of functions we're going to solve, because it is possible to have like f of x, y to be like x1 squared minus 3x to the 1/2. So we're not going to solve any of those. We're only going to focus on linear equations. Okay? So that means the dx dt is going to equals to like ax plus by, and dy dt is going to be another constant, let's say cx plus dy. So these are the functions we're going to be solving, which is technically what you did before. And this will create the matrix A, which is going to be A, B, C, D. Now the part that is new is going to be this. Notice that if you divide this equation over these ones, the dt will cancel, and you will have dy dx, which is there usually denoted by the rate of change. Okay? And in the other side, you will have cx plus dy divided by ax plus by. Remember that the derivative represents is the velocity, so you can think of this as the component of the velocity, okay, of a particle that is moving on the xyz plane, that is moving in the xy plane, which is technically in 2 dimensions. Now, usually the xy plane is also called the phase plane, and hence the name of what we're gonna do right now. If you remember what we did way back at the beginning of the class, remember that dy dx represents technically the slope. And what we did before in the xy plane, you have something that were called direction fields. Okay? And you have something that looks like this. Okay? So one by itself, so this is a trajectory. So if you only pick one of them, this is called a trajectory. But if you take into account all of them, which will be now all of this, so then all of them together is called the phase portrait. So technically one of them is only the trajectory, and all of them combined is a phase portrait. So what we're going to do in this section is how is this going to look depending on which eigenvalues you have. To solve the problem is exactly the same thing you did before. It's nothing new. The only thing we want to analyze now is what happened to this, in particular to the equilibrium points, depending on the eigenvalues you have. Also, recall from chapter 9, what we did at the beginning of chapter 9, you have this on the test. Since we're only dealing with 2x2 matrices, there is a fast way to find the eigenvalues. So remember, if A is a matrix that is 2x2, then the eigenvalues are going to be found by solving this equation. Lambda squared minus the trace of A plus the determinant of A is equals to 0. We talked about this in the past. Recall that if you solve this equation, you technically had 3 choices. Case 1 was that lambda 1 and lambda 2 are 2 distinct real numbers. So that was the first case. Case 2 is that lambda 1 and lambda 2 are 2 conjugate, or they are 2 complex numbers. And then case 3, which we didn't do before and we're not gonna do it still, as you're gonna mention it, is you have one repeated eigenvalue, which means that lambda 1 is equals to lambda 2. So we're only gonna still focus on case 1 and case 2. All right, case 1 is where the 2 are real eigenvalues. Now remember, if the numbers are real, they could be positive or could be negative. And here, lambda 1 and lambda 2 are not equals to 0. Remember that in this case, the solution looked like this. X of t was equals to c1 e to the lambda 1t times one eigenvector plus c2 e to the lambda 2t times another eigenvector. So the first thing we should notice here, so this would be a subcase. You can call it case A. So if lambda 1 is bigger than lambda 2 and they are positive, notice that this is going to go to infinity. This is going to go to infinity, so is this. So therefore the equilibrium point is going to be unstable. The equilibrium point sometimes is also called a node. So that means that the node, which usually is 0, 0, is unstable. And unstable means this. If the equilibrium is right here, let's say 0, 0, that means the trajectories, all of them are going away from the equilibrium point. So everything is going out. So this is unstable. Part B, if lambda 1 is less than lambda 2 is less than 0, which means both of them are negative, then in this case the equilibrium point will be stable. And unstable equilibrium point will look like this. Notice how all the trajectories are converging to the equilibrium point, which is right here. Okay, so this is what it means to be stable. Now a third case will be this, where one eigenvalue is positive and the other one is negative. So in this case, the equilibrium point is going to be called a saddle point. And it will look like this, where one set of the trajectories are converging to 0 or to the equilibrium point, and the other ones are going away or divergent. So this will be a saddle point. So to recap, if you have two real eigenvalues, the solution is going to look like this. But these are the three things that could happen to the equilibrium point. There is actually one more part, but these are the only three things you should need to worry for the exam. All right, so now let's look to case 2, where the eigenvalues are complex. Now, in the case where the eigenvalues are complex, remember you actually only need to use one of them. Doesn't matter which one you use. And lambda was equals to r plus mu I, or you could use the minus, either one is fine. And this is the real part, and this is the imaginary part. Okay. Then the solution looked like this. Remember, x of t was equals to c1 e to the rt times a cosine mu t minus b sine mu t, okay, plus c2 e to the rt a sine mu t, and then plus b cosine mu t. So you did this in the last test, so this is not new. Where, remember that a and b were eigenvectors, so eigenvectors. Now again, just like when the two were complex, you're gonna have technically three cases here. So subcase A, if lambda is equals to just mu I, which means that r is equals to 0. So then this is called a pure imaginary, because the real part is not there. And this one, the equilibrium point, in this case the equilibrium point is going to be stable. And when you do the face portrait, it's technically just a bunch of circles. So this is stable. Now case B, if R is positive, then the equilibrium point, I'm going to call this EP for equilibrium point, and the equilibrium point is going to be unstable, and this is called a spiral, and the path looks like a little like a spiral. So you have the point here, and then this will be a spiral that is going out. The last case, it will be, well, if R is negative, then the equilibrium point now is going to be stable, and it's also going to be a spiral, but this one is going to go inwards. So the spiral is going to like this, but now this time is going the opposite direction, is going inside, and this is considered stable. All right, so finally for this page, this table summarizes everything we have done. So if it is real and negative, then you're going to have a stable node. Real and positive is going to be unstable. Opposite sign is a saddle point. Pure imaginary is a stable center, which was this case. Complex with positive real part is an unstable spiral, which is this one. And then complex with negative is stable spiral, which is this case right here. This one should actually be going the other way. Now we're going to take a look at the examples that I did before. So you should take a look to the notes that we did in chapter 9 before. But we have an example like this before, where x1 equals to x1 plus 3x2, and x2 prime was equals to 4x1 plus 3x2. And in this case, A was equals to 2, 3, 4, 3, and the eigenvalues where lambda 1 equals to 6 and lambda 2 was equals to -1. Again, you should check that. So you still need to know how to do this. So after this, and when you write the solution, remember the solution will be like this: C1 3, 4 e to the 16 plus C2 1 minus 1 e to the minus t. Again, this is what you did before, and you still need to know this for the, at least for the final, well, for test 3 also. So the only new thing here is you need to categorize the equilibrium point, which clearly you can see that the equilibrium point is going to be just a point 0, 0 from here. Okay. So here the two eigenvalues you have is one is, I mean, both of them are real, but one is positive and one is negative. So that means that you have a saddle point, which is unstable. Okay. So this is the part that is new, I guess. We also did a example like this before. This was the last example we did in that section. Let's say that x1 prime was equals to 2x1 minus 5x2, and x2 prime was equals to x1 minus 2x2. Here the value for a was 2, -5, 1 minus 2. And once you find the eigenvalues, in this case, you have lambda plus 1 is equals to 0, which implies that lambda was equals to plus or minus I. The answer in this case was x of t is equals to c1 phi cosine t, 2 cosine t plus sine t, and then c2 phi sine t, this was 2 sine t minus cosine t. But the part that is new is this, since these are pure imaginary, then this implies that the equilibrium point is a stable center. Okay, again, this is the only part that is technically new. All right, and that's it. This is the last video, I think so.